Doesn't know when you have the base for quizzes in.
I'll have them in later this afternoon. All right, start a new chapter. Chapter 3. This chapter is about log and exponential functions, or exponential and log functions. So when we think about exponential functions, so we have 3 functions we're used to seeing here. We notice that the leftmost equation that I have graphed up here, that's a linear equation, right? Y is equal to X, we recognize that. We have our quadratic equation here, which is X raised to the 2nd power. We know we were just working with polynomial functions. Those are base X raised to some power, some integer positive power. But notice what happens when I start talking about an exponential function. Where's the variable at in that case? It's to the power, right? The variable, the part of the function that is actually changing, is up here in the power position. That's different from what we had in our previous functions, where the variable that was changing was the base, right? The base is what was changing. So when we are looking at exponential functions, the base A is our constant, and the variable that changes in the in an exponential function is up there in the power position, in the exponent position. All right, that's what kind of sets it apart. Now, when we think about our exponential functions, again, we have A, which is going to be the base. A is going to be constant. The variable is in the exponent position. And our constant, our base A, has got to be positive and not 1. Those are the 2 requirements for the function, that the constant must be positive and not 1. Now, when we rethink about this, right, when we think about those 2 requirements, if I have let me rephrase it. If I were to let A be negative or less than 0, right? If I was to let A be negative and I raised it to some power, let's say, if I rewrite this from its rational form into its radical form, so I take it from a fraction into its square root portion, this becomes the square root of negative A, right? You all remember how to move back and forth between rational exponents and radical parts? The denominator becomes the index and the numerator is the power, all right? So can I take the square root of a negative number and get a real value? No, right? That's not allowed. That's no, okay. If I had negative A raised to, say, 3/4, that would be the 4th root of negative A cubed. Remember, the denominator is the index, the numerator is the power. So negative A raised to the 3rd power is still negative. Can I take the 4th root of a negative power?
No.
No. Okay. So the point of this is to say, this is why A has to always be positive, because we're dealing with exponents that are these values that we have right here, right? We're dealing with potential values that could be 1/2, 3/4, and so forth. And the other requirement that we have is that A is our constant. A can't be equal to 1. The reason we have that is because, remember, A is our base. What if I had 1 raised to the 10th power? What would that be?
1.
Okay. What if I have 1 raised to the 100th power?
What?
Like, that's boring, isn't it? Right? It doesn't change anything. And if the variable that we're interested in is the exponent always changing, and I have a base of 1, then there is nothing that changes there, right? Okay, so this is why we have this criteria that A has to be positive and A has to be not equal to 1. When we graph our exponential functions, this is what they look like, okay? Make sure you have this written down. Our exponential functions can look 2 ways, depending on what A is, or depending on what the exponent is, I should say. In one, on the left-hand side, when the exponent is positive, the function is increasing. On the left-hand side of the function, if the exponent is negative, then it's decreasing. The characteristics of these functions say that the domain of the function, all the possible x values, are going to go from negative to positive infinity. But the range of the function says that there's an asymptote there at y is equal to 0. So in other words, the range would be from 0 to infinity. We have a horizontal asymptote, like I said, at y is equal to 0. We have a y-intercept at 0, 1. You need to make sure you have all this information written down. We're going to use those characteristics to graph it in a few minutes. And like I said, you have 2 different ways to look at this. You have a increasing exponential function, and then you have a decreasing exponential function. Remember, what was the test? What was the line test that we used to test if a function was 1 to 1?
Vertical line test?
Not the vertical line
Horizontal.
test. The vertical line test, whether or not it was a function. Horizontal line test determines whether or not it's 1 to 1. All right. And so these are 1 to 1 functions. That's important because that's how we end up with log functions. Exponential and log functions are inverses of each other. Okay. All right. Almost got that written down?
Almost.
The next thing that we want to talk about, you don't have to write this part down in yellow, but the next thing that we have to talk about is the fact that we're going to talk about base E, right? Which is our natural base E. So in that E comes from, it's defined by taking 1 plus 1 over n raised to the nth power. Again, you don't have to write this down, but that's where we get this value for E. Does anybody know what the value is for E? What? 2.7-ish, right? 2.71, blah, 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 blah. Okay, why did I say blah, 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 blah? Because it's irrational and it never ends, right? Is there another number that we know that's irrational that never ends?
Pi.
Pi, okay, so E is a lot like pi. Only we use E a lot in calculus, all right? And if you forget what E is, what the value of E is, you just go push the button E on your calculator and it's going to spit out 2.7, blah, 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 okay? Now, in calculus, we can actually find what E is by taking the limit as n approaches infinity, which is something to consider. So here we've got the recursion of it, right? And yep, it's 2.718, blah, 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 okay? So we want to just consider that E is going to be, even though it's going to be a letter that we're going to look at, it's a base. It's a constant. Just like pi is a constant. It's an actual number. All right. Now, because we already talked about transformations in trig, right? What do I mean when I say transformations of graphs? Where we have those shifts left, right, up, down, amplitude, right, stretching, I think is another way to think about it. okay? And we need to understand how those transformations affect all graphs, all parent functions. So when I ask you to graph these exponential functions using transformations, we'll use kind of what we've already gone over in trig. So here I have the function f of x is equal to base 5 raised to the x plus 1 power, okay? And all I'm going to look for when I graph these is I'm going to show you what I'm looking for. It's not anything too terribly big, but it's helpful to write down what the base is. Our base that we have here is equal to 5. Okay. Our base is going to be 5, and so we actually are going to be looking at this. Also, let's see, the numerator, the exponent that's up there is positive, yeah. So, or x that's up there is positive. So this would be an increasing function. I just want to know that I can get the shape right. Remember the characteristics that we were looking at above? We had a y-intercept occurring at where? 0, 1. And we have a horizontal asymptote occurring at y is equal to 0. Those are all the base characteristics of this function before I ever do any transformations on it. Now, what effect does this x plus 1 have on the function? It's a horizontal shift, right? Does everybody see that that's a horizontal shift because it's happening inside of the function? It's happening up there with the variable, okay? So it's a horizontal shift to the left by how much? Okay, so all I'm interested then when I graph this is going to look like this. I had the original y-intercept was occurring at 0, 1, but I'm shifting it to the left now. So I have a new point that is going to be at -1, 1, correct? So that intercept that was here at 0, 1 just shifted to the left by 1. We still have an asymptote here at y is equal to 0 because my horizontal shift left right does not impact that asymptote, does it? Because all I'm doing is shifting this function from the left to the right, so it doesn't affect that horizontal asymptote. And finally, if I know that this is an increasing function, then I just have to draw it passing through the point, although mine doesn't look that pretty. There, passing through the point. That's all I'm interested in. 3 things on a test, okay? I want you to get the asymptote right. I just want to shift that intercept over, left, right, up, down, something like that, and then give me the shape, the general shape. Okay, that's all I'm actually looking for in these, but that gives us an idea of what this function looks like. Now, if you did it on your graphing calculator, I'm not playing around at all with how sharply this thing increases. I just want to know if it's increasing versus decreasing is all I'm interested in. So let's look at this next one over here. The function e to the x minus 3. So I have a base e. I also know that that exponent is positive, so this is increasing. I have that original y-intercept at 0, 1. I have a horizontal asymptote at y is equal to 0. That's the characteristics of this base function. Now, what effect does that minus 3 have on this function?
It should.
Shifts it down by 3, correct? So that's subtracting or adding outside of the function, right? It's outside of where the variable x is located at. All right, so this is going to shift it down by 3. So I had my original point here at 0, 1. I also had my original asymptote at y is equal to 0, correct? I like to move the asymptote first. I'm going to move the asymptote down 1, 2, 3. So I have a new asymptote here at y is equal to -3. And that point also moved down 3. So it is here at -2 on the y-axis. Now this is an increasing function. So I can draw it like that. Okay, that's all I'm looking for. No biggie. I know you can graph these in your calculator. I'm looking for the asymptote. It's easy to graph them using transformations, taking that one point, moving left, right, up, down, and so forth, okay? And then increasing versus decreasing. Okay, questions on that? Exponential graphing is pretty easy. We all remember how to do transformations, right? Yes? Okay. Now, let's go over some of these rules just in case you forgot them. We have the product rule, right? The product rule for exponents, since we're talking about exponential functions. The product rule for exponents says that if their bases are the same, then we add their exponents, right? If their bases are the same, then we add their exponents. Quotient rule says that if their bases are the same, we're going to subtract their exponents. I typically handle those a little differently, but still you're just taking the difference of those exponents. The power rule says that if I have a base raised to a power that's also raised to another power, you multiply those two powers together. The negative exponent rule. We talked about this briefly, but it becomes very important for us as we move on. The negative exponent rule has to do with the location of the base. So here, if I have base A in its, let's call it numerator position, if we're thinking numerator versus denominator, if I have x raised to the negative A, then if I move it now into a denominator position, so it's not where it originally was. If I move it to the denominator position, it changes the sign on the exponent. It's all about the sign of the exponent. So that's the negative exponent rule. And the other rule that we're going to look at and practice with is what we call the one-to-one property. That property says it allows us to say that if I have two bases that are set equal to each other, that are the same, two bases that are the same, that are set equal to each other, then I can take their exponents and I can set them equal to each other and I would be able to solve, because they would have to be the same exponents, wouldn't they? If the two bases are the same and they're equal, then we're saying that these two exponents have to be set equal to each other because they would be the same. It's a property that we're going to use. So we have a couple of examples that we're going to look at here. I want to solve these exponential equations using our exponent rules as well as the one-to-one property. So the first example says 3 raised to x plus 1 is equal to 81. What you want to recognize here is I already have a base of 3 on the left-hand side. Can I rewrite 81 as a base of 3 raised to some power?
Yeah.
What is it? 3 to the 4th, right? 81 is 3 to the 4th. Okay, so I would have 3 to the x plus 1 is now equal to 3 to the 4th power. So by writing it in its exponential form with the same base as what's already on the other side, we can apply the one-to-one property. which says, all right, if their bases are the same, we can set their exponents equal to each other and solve. And I would find out that x is equal to 3, okay? How about the next one that we have up there? 4 to the 2x minus 1 equals 8 to the x plus 3.
Could we just take down the two exponents and solve for x that way?
I can't apply it that, I can't apply the one-to-one property because my two bases are not the same, 4 and 8 aren't the same.
So could you take the base, make 4 into 2, since 2 times 2 to the power of 2 is 4, and then 8 would be 2 to the power of 3.
Yes, rewrite these as a power, as a base of 2 raised to their power, right? So 4 is 2 squared times the 2x minus 1 that was already there. And 8 is 2 to the third power times the x plus 3 that was already there. So although I have a 4 and an 8, you have to break it down to where you can rewrite it as two bases that are exactly the same. So now we have 2 and 2 as the basis, so we're going to write these as 2 times 2x minus 1 equals 0, 3 times x plus 3 is equal to 0. Distribute. 4x minus 2 is equal to 3x plus 9. So I'm going to subtract 3x and I get x. I'm going to add 2 and I get 11. Okay? Questions on that? All right, let's look at this last one here. E to the negative x squared is equal to e to the x to the second times 1 over e cubed. So I have e to the negative x squared. That looks like a potential quadratic equation, okay? So let's simplify the right-hand side first. E to the x to the 2 becomes what? Because it's a power to a power, right? So it becomes e to the 2x times, let's take e over, or 1 over e cubed and rewrite it as e to the negative 3. Using the negative exponent rule. Now we still can't technically apply the one-to-one property because that says that I have a single base on the left equal to a single base on the right. And I got two bases on the right. But I can rewrite the right-hand side as e to the 2x minus 3. I can add those two exponents together, right? Because they're the same, I'm multiplying their bases. E times e says I'm going to add their exponents. Now I have a single base e on the left equal to a single base e on the right, and I can apply the one-to-one property. So I would have negative x squared is equal to 2x minus 3. And I would need to solve it from here. Okay, I'm going to let you solve this quadratic equation. Move negative x squared over to the right so that it's positive, factor it. Since it's now set equal to 0, set each of your factors equal to 0 and solve. Okay, do you all get 1 and -3 for your values of x? When you factor this, 1 and -3, because it factors into x minus 1, x plus 3. Plus 3 minus 1 gives a plus 2, okay? All right, so those are some examples of how we can use the one-to-one property to solve our exponential equations that we're just kind of looking at today. That's specifically using the one-to-one properties. And it's using our rules of exponents that we were talking about, okay? So some applications of our exponential functions. The most classic one would be about compounding interest. Do y'all understand what compounding interest is? Can anybody explain it to me? What is, go ahead, Isaiah.
So like, say you have like $10 with a like interest rate of like 10% for like a year or whatever. Every year you get an additional 10% of that $10, and then on that second year it's that.
You're right.
Second year it's like, say it's okay, so 10% is $11, right?
Mhm.
Second year you get 10% of $11. Third year 10% of whatever that $11. Yeah.
Right, so you
Add it.
keep getting more and more, right? So your simple interest was just 10% of $10 for the rest of the life that it's invested. That's it. $10, 10% of $10, no matter what. Compounding interest says that I have an interest rate, right? I'm going to take the interest rate on the amount that I have invested or borrowed. And each year or each time it's compounded, I am going to recalculate the interest based on this new sum. Okay? Your credit cards are generally done at a compounding interest, right? Mortgages, home loans, car loans, all of that stuff is compounding interest. Okay? And it is a process that is exponential. So compounding interest when you invest something is really good, right? That's a good thing. You want your money invested so that it gets compounding interest because it's going to grow exponentially. That's always a positive thing. The negative part is understand that when you borrow money, it also is compounded and it will exponentially grow. The amount of money you have to repay grows exponentially. It would be interesting for you all, it would be eye-opening, right? For you all to take a mortgage, let's say you had a $100,000 mortgage on a home, and you took out a 30-year loan for that $100,000. At the end of 30 years, you will pay substantially more than $100,000 that you originally borrowed, okay? It's interesting. It's a little scary at first, but don't worry, just do it anyway. It's a good place for your money. Okay, so what we're going to look at here is compounding and n, which is the rate or the value of which we are compounding, on what series we would be compounding in it's the time at which we're compounding per year, is what I'm trying to say. So we can compound quarterly. If I compound quarterly, how many times will I compound in a year? Okay, 4, right? If I compound monthly, how many times will I compound in a year? Right? If I compound semi-annually, how many times do I compound in a year? 2, semi-annually, right? Twice a year, okay? Compound daily, that would be 365. Sometimes there are credit cards that will start to compound daily if you don't pay it off within you don't pay it off in the first 30 days. Watch out for those. That's what N stands for. N is the amount we're compounding by per year. T is always going to be the time we are taking the time that we have it invested or we've taken the loan out on per years. So T is always in terms of years, okay? R is always going to be our interest rate in terms of the decimal value, okay? P is our principal, so the P is generally what you are investing. P would be the principal, the amount I invest or the amount I borrow, and A is the amount after that value, okay? Now, the other formula that you need to understand about is compounding continuously, okay? Compounding continuously right there. We call this PERT, kind of because it looks like the word PERT, right? It's easy to remember. All right, so this is basically saying that the base that we're going to use is going to be a base E. All right, so the principal times base E raised to the RT, the interest rate times time. Instead of compounding, it's a different type of compounding. So what we want to do here is we want to compare which of these two investments is going to yield the greater return over 4 years.
Is that NT, the exponent NT?
Income, in this one it is, NT. This is RT. PERT. So we want to compare which one is going to be better or which one results in a better return using these two formulas. So we have a $600,000. No, we have a $6,000 investment. We want to know what A is. We are investing this for 4 years. We are compounding quarterly, so the rate is 0.0825 for the interest rate there. And N on that 8 1/4 interest rate is going to be 4.
So then you just plug it all in.
Yes, so I'm going to write the formula down here. So I know I'm looking for A, right? I want to know what the balance is after I've invested this. So it would be 6,000 times 1 plus 0.0825 over 4 raised to the 4 times 4. We want it to the nearest decimal. We want it to the nearest hundredths place is what I'm trying to say. Then we're going to come back in. We have an interest rate here for PERT at 0.083. We are still investing for 4 years. So make sure that you can get these values here. You should have $8,317 and I think 84 cents for the continuous. I mean for the quarterly, and then you have $8,362.52 for PERT.
part would be a little greater.
Which makes sense because it's gonna be a continuous compounding. As opposed to only compounding 4 times a year. Remember, the compounding part is I get to earn interest on this new amount 4 times a year. They recalculate it. Can everybody get those two numbers using their calculator? Because really, I think at this point, it's a calculator problem, just making sure you can throw it in a calculator and get the numbers right. When all you're asked to do is find what the available balance it will result in, it's a straight formula problem. When we get into solving these equations, we are going to reevaluate, we'll reapproach these problems a little bit differently. But this particular problem is just simply asking you to figure out how much your investment would be after 4 years. And there's not a single thing, there's not any savings account or anything out there right now where you're going to earn 8.25% or 8.3%, which is kind of funny. When I was young, my mother used to make me call around to the banks and find the best interest rate on a CD for like a year or whatever, and then I would go and I would invest it there. They don't have the very good rates anymore. Isaiah, you want to pipe up?
I mean, there's some things you can do where you can get like I have an annual 10% compounded interest on my retirement fund accounts through like a stock brokerage.
Yes. So in the stock market is about the only place where you're going to average. I think that my guide tells me when we go back and look at it, on average, it's like a 10 or a 15% rate of return in the long run.
Yeah.
You got to play the long game for that. If you're looking for like a short-term investment, there's not many out there that are going to return. And because there's no interest rates right now that are that high. If you think about car loans, even house loans, right? House loans and car loans are way down, right? You can get a car loan for like 3.25%, or a home loan, I think you can refinance for like 3.5 now or something, 2.5, 3.5. So that's a far cry from what you would be getting off of that. But that's a good thing if you're borrowing money, isn't it? Good thing because you can borrow the money a whole lot cheaper. Bad thing if you're trying to invest money quickly. Okay, things to think about. All right, let's look at this one. This is kind of interesting. I haven't looked at this problem in a while, and there is a lot of talk in the news right now about inflation and what that means, right? Okay, and I can't remember what they're projecting the inflation rate to end up being, but this is an interesting look at a problem that I pulled several years ago, I think. The annual rate of inflation averages 4% if it averaged 4% over the next 10 years, then the approximate cost of goods or services during any year in that decade can be modeled by this formula here, right? Cost C of T is equal to P times 1.04 times the T, which is our time. The price of an oil change for your car is presently listed at $23.95. We want to estimate what that price is going to be 10 years from now. Okay. All right, so we're given the model. The model came from flat out right there. So the cost in terms of time is equal to whatever it costs now times 1.04, because you would pay 4% more than you currently are. So that would be 100% plus 4 more percent. That's how you get the 1.04 times the time that we're looking at. So my present cost, right? The present cost for an oil change is $23.95. Is that about right? It's not. What is it now?
$60.
I mean, it depends on where you go.
Probably depends on the car too, doesn't it? All right. So you ought to put yours in, put 60 in, see what it's gonna get, right? If you know what,
Are we doing like baller, like full synthetic here? Or are
Right.
we doing like some cheap, like $23 oil?
We should figure it out, right? Because if you have like the nice fancy cars and you gotta go to the special oil change place, right, then it's gonna be more. If you go down to Jimmy Lube, I don't know. All right, now time is gonna be 10 years. All right. So let's plug it in. 2395 times 1.04 raised to the 10th power. Did you do your $60?
88, 81.
Reagan, I heard you mumble back there about inflation. Do you know what it's, have you heard? I can't remember. I can't remember if they're saying it's gonna be 4% or 3% for some reason.
Like 3.5.
Okay, that's what I thought. So this is us, in 10 years. It does. It really does. The price of- Yeah. Okay, what do we get? Do we get 35?
35.45. That's what I got.
So it's gonna be $12 more to get an oil change in 10 years? And that's just an oil change? It's interesting, right?
That's how much the oil costs.
Okay. Where Stan over here is gonna pay $80, he said, right? I may, you're gonna pay, I don't know, if you get the premium
It's like $50 for me, like,
currently?
Yeah.
All right, so put it in here times 1.05 over 10 years, right? Go right. Last one we're gonna look at as far as modeling, and then we're gonna do a little bit of modeling towards the end of this section anyway. So I'm gonna fill in a little bit of this. It says immediately following an injection, the concentration of drug in a bloodstream is 300 milligrams per milliliter. So I know that most of you are engineering students. This is a biology question though. So after 10 T hours, the concentration is 75% of the level of the previous hour. I didn't realize, most of you who are in biology probably realize this, but our medication depletes. This is how they determine, it's based on it's an exponential function is what I'm trying to say. So that's how they determine how much like Advil or ibuprofen you need based on the decay in your bloodstream, how much is going away, which I thought was interesting application of an exponential function. All right. So if we have this idea here, if we know that this is decaying, the concentration is 75% of the previous hour, and we want to come up with a model for the concentration of the drug, we're going to take a little bit of this information that we have given here. So the concentration of the bloodstream starts out at 300 milligrams per milliliter. And we also know it's 75% of the level of the previous hour. We can create a model for the concentration based on that information to look like 300 times that 0.75 over time. It almost looks exactly like our inflation rate problem we did a minute ago, or PERT, right? We've got the initial amount times some base raised to a time. It's basically how these kind of work out. So that's what our model looks like. What's the concentration of the drug then after 8 hours?
Be about 30 milligrams.
That's what I get. So just some applications that are useful. There is an argument in some of the realms of mathematical sequencing to use exponential functions instead of quadratic functions to kind of build your repertoire on, because they are more applicable than a quadratic equation in essence. There's an argument for this. So here's a bunch of examples on exponential functions, okay? Questions on applying them? Questions on these examples? These are fairly straightforward right now because we're just using the information and plugging it directly into the formula to kind of apply it. All right, make sure that you understand how to apply the one-to-one property and what I would be expecting from you from graphing. Okay? All right. So the next thing that we're going to do is we're going to talk about log functions. So log functions, here's our definition. Make sure you get their definition written down. So a log function and an exponential function are inverses of each other. I can write one in terms of the other. That says y is equal to log base a of x y is equal to log base a of x if and only if x is equal to a base a to the y. That if and only if is a one-way street. It means it only works if they both are related, right? If and only if. Y equals log base a of x, if and only if x is equal to base a to the y. That's the definition that we're going to use. And you'll notice that base a has the same requirements that it did for an exponent. It's got to be positive, it can't be 1. All right, because that's the important part. We're going to move on. And we're just going to practice rewriting these. These happen to be equations, but these we could rewrite expressions. We're just going to rewrite them and take them out of their log form and rewrite them in their exponential form. So I always start with the base. Base 2 raised to the 6th power is equal to 64. Base 2, read from the log part of this, base 2 raised to the 6th power is equal to 64. And in fact, yes, 2 to the 6th power is 64. All right, so we're just rewriting these. We're practicing how to rewrite something from its log into exponential or exponential into log. So for this one, this next one, this says log base 9 of 1 over 81. Maybe we want to take this and let's rewrite this part right here. I'm going to put it in parentheses. That part right there is called the argument. Okay, so I'm going to rewrite the argument as log base 9 of 81 to the negative 1, right? Or I could have written it a little bit differently. Oh, sorry, I lied. I don't want to do that yet. I'm going to lead you down the wrong path. Let's not do that yet. We'll explore that in a minute. Let's just rewrite it using its exponential terms. Base 9 raised to the negative 2 power equals 1 over 81. I'm just going too far. We'll just leave it like that. Practice with that part. You all agree with that? Yep. Okay, because I could rewrite 9 to the negative 2 power as 1 over 9 squared, couldn't I, using the negative exponent rule? And 1 over 9 squared would be 1 over 81. All right. What would this log 64 of 8 equals 1/2? So what's our base here?
64.
64 raised to what power? Equals what?
Okay.
8. Remember, we can take a function, we can take a base, we can take a rational exponent and rewrite it in its radical form. This is the square root of 64, and the square root of 64 is 8. Okay? All right, let's go backwards now. Or let's go in the opposite way. So right now, I want to take it from its log form and rewrite it in its exponential form. So what's my base here? All right, so I have log base 5 of 625 equals the exponent 4. Log base 5 of 625 is equal to 4. So the next one says the cubed root of 64 is equal to 4. We want to rewrite these in their exponential form. So 64 is raised to what power here? 1/3. All right, so we've set it up. Now I can change it from its exponential form and put it in its log form. So this is log base what? Equal, log base 64 of what? 4 equals 1/3. Okay, last one. 5 to the negative 3 is equal to 1 over 125. What's the base? So this is log base 5 of 1 over 125 is equal to negative 3. So all we did here was practice moving from one into the other, right? Rewriting as logs or exponential forms, whichever one they ask us to do. So just like with our exponential rules, we have some properties that we're going to apply for our for logs. So our properties of logs are listed for us here. Take a minute, make sure you get them copied down. And then there's 2 of them that I want to talk to you about. Either one. So can you do just type log? No, okay, so no, there must be a function. Is there a function in there for it? I don't know how to do it in the face. That'd be interesting to find out. All right, so we have these in here. And what we're going to look at, what I want to point out to you are these last 2, the inverse and the one-to-one properties for logs. For the inverse property, what we're looking at here is when the base of the log and the argument's base are the same, when the base of the log and the argument's base are the same, that's equal to the exponent. Okay? When the base and the base of the log are the same, this is another way for us to look at it. So in its log form, log base A of A is equal to X. In its exponential form, base A of log base A is equal to X. See the property there? Okay, so those bases had to be the same. The one-to-one property is similar to what we had before with our exponential functions. And what this one looks like is if I've got log base A equal to log base A, then I can set their arguments equal to each other and solve. Okay? Because the arguments are going to be equal to each other. That's our one-to-one property. Okay, so let's apply some of these things here. The idea is for us to practice doing this without a calculator. So one of the newer updates that happened, I don't know, like about 10 years ago probably, or maybe 5 years ago on the newer calculators is that you can change the base, all right? But that wasn't like, Nick, I'm gonna pick on you. Your calculator, I'm pretty sure, is not gonna do a base other than very specific ones. So we had to know, okay, well, how could I find this value? How can I find this number without a calculator? And we can do it using our properties from above. So in other words, by hand. So if I have log base 7 of 49, and we wanted to apply our inverse property, I can rewrite this similar to what we did above. Log base 7 of 7 squared. So I want to rewrite the argument as some base that's the same as the log base. Now, if I do, then I can see these two things are the same, and therefore the answer is just 2. Okay, let's try that again. For this next one, I have log base 3 of 1 over the square root of 3. Let's rewrite this in its exponential form. This looks like log base 3 of 3 raised to the negative 1/2. Is everybody good with how I got 3 raised to the negative 1/2 there? No? So 1 over the square root of 3 would be 1 over 3 to the 1/2, right? If I take the square root and rewrite it in its rational form. And then if I take that denominator 3 to the 1/2 and move its position, it becomes a negative exponent. You see that now? Okay, does everybody see that? So I rewrote 1 over the square root of 3 as 3 to the negative 1/2. So applying the one-to-one, applying the inverse property said those bases are the same. So the answer is negative 1/2. How about this one over here? It says base 3 log base 3 of 17. Okay, this is still the inverse property. Base 3, oops, base 3 and log base 3 are the same, so the answer is just 17. Now, those are bases, just any types of bases. But we have two special bases. We have base 10 and we have base E. And base E is going to be our natural logs. And we will forever call them natural logs. because they're base E, and we use them almost extensively in calculus, the base E, natural logs. And so the natural logs are log base E of x, but we abbreviate that by just ln of x. Now, I will always write for you, my ln's will always look like a cursive L, okay? Because otherwise it gets a little hard for you to tell whether I'm doing a 1 or an L. So I changed mine and I write it in cursive. So natural log of x. And if you look at your graphing calculators, you actually have a button that is an ln button. And then above that, you'll see that it is e raised to the x power. All right, so those are the two that are related there. That's the natural log. Common log is log base 10, and we write it just as log, no base 10. Like it's understood that it is a base 10. So natural log e, or the natural log is base e. Log base 10 is just the common log. Why do you suppose it might be common? What do we know that's base 10? Like our number system,
Yeah.
right? At 10 fingers, that's probably why we have a base 10 number system. Okay, so common log is base 10. If you look at your graphing calculator, you'll have an log button, and then above that, it'll have 10 to the x. All right, so those are the two that show up there. So let's apply those two new concepts to see if we can simplify what we're looking at here. I have log of 100 without a calculator. How can I rewrite it to show that? I'm going to rewrite this as log base 10 because it's understood to be 10. Can I rewrite 100 as base 10 raised to some power? 10 to the second power, right? So that would be 10 seconds. So now my two bases are the same, and that's actually equal to 2. See if you can answer those two questions on your paper. All right, do you get 1 for the natural log of e? Okay, that's going to be so common that you're going to want to just recognize it and memorize that, right? The natural log of e is actually just 1, and it's because the natural log is log base e of e to the first power, okay? Then we have the e to the ln of x of 7x squared. E and ln cancel each other out. I just wrote it so that you can recognize it because ln e is log base e. So those two bases are the same, giving me the argument of 7x squared. Now let's do a little algebra on those things. So what we were just practicing was the inverse properties, how to simplify these guys without a calculator. Now let's use the one-to-one property that we were looking at above. This is on these, on any of these that we're looking at. So I have log base 5 of x plus 1 is equal to log base 5 of 6. The only thing you have to check when you want to apply the one-to-one property is that these are both the same bases. So they are, they're both base 5. And so I can just take their arguments and set them equal to each other. X plus 1 is equal to 6, or in other words, x is equal to 5. Okay? That's just applying that.
How did you?
Okay, let's look at another one. Log of 2x plus 1 is equal to log of 15. Right, the logs are the same, so we apply the one-to-one property. They're both log base 10, so 2x plus 1 is equal to 15. Or 2x plus 1 is equal to 14. Therefore, x is equal to 7. All right, and y'all do the last one right there. You get x is equal to plus or minus 5. Yeah? Okay. Okay, so that's just simple ways for us to apply the one-to-one property, just like we did before with our exponents, only now we're looking at logs. We just want to verify that their bases are the same to be able to apply that property. Because we're going to talk about solving exponential functions and log functions, not today. So now let's look at the graph of our log function. Notice that on our log function here, it's an increasing function. The one that I have drawn is an increasing function. This is log base a of x. And it crosses through the point 1, 0. It has a vertical asymptote at x is equal to 0. So the domain of the function is going to be from 0 to infinity, and the range is going to be from negative to positive infinity. Okay. Now, how are these two related? Remember, I told you that exponential and log functions are related. We know that if they are inverses of each other, then the x and the y things, right? Almost all things x and y just switch. Okay. So notice that for the log function you're writing down here, we have an x-intercept of 1, 0. But on the exponential function, we had a y-intercept of 0, 1. So those x and y values switched. The domain of our log function, 0 to infinity, negative infinity to infinity, the domain and range of log are the inverses for the domain and range of the exponent. In a log function, you have a vertical asymptote at x equals 0. In an exponential function, you have a horizontal asymptote at x is equal to 0. So these are true inverses of each other. Their x and their y components switch. When you have inverse functions like this, they are symmetric across this asymptote, we'd say, or this imaginary line of y is equal to x. Remember how we have symmetry across the y-axis, or we have rotational symmetry, right, across the origin. Inverse functions have a symmetry across y is equal to x. So let's look at this problem right here. For this problem right here, I'm only interested in finding the domain of the function at first. And when we want to look at the domain of the function, it's really just going to be where the argument, so the domain that we're looking at is where the argument is greater than 0. So we solve it, we treat it almost as if it's an algebraic property. And remember, the argument is this component here in parentheses. That's the argument of our function. So I would have x plus 6 greater than 0. So I'm going to solve that as if it's an inequality greater than 0. And I would find that as long as I don't divide by a negative number, x is going to be greater than -6. So the domain has to be from -6 to infinity. Now, what if I wanted to graph the function? What if I want to graph this function?
When you have to move over to the left 6.
Okay, so we know, let's write down some of the things that we know first, okay? I know that the base is 5, so it's positive here. Okay, I would assume then that this is an increasing function. I know that before I ever translate it, I'm going to have an x-intercept at 1, 0. And I know that I have an asymptote at x is equal to 0. So just like Javi said, the x plus 6 is going to shift this thing. Which direction?
To the left.
To the left by 6, right? We're just going to shift it to the left by 6. So to sketch the graph, I'm going to move the asymptote first. That means that my x-intercept now shifted to the left by 6 as well. It's going to cross through -5. This is an increasing function, and that's about all I have to do. Now, what if I wanted to know what the inverse of this function was? If this function starts out as a log, the inverse function is going to end up being what? An exponential function, right? Okay. So if I start with the function y is equal to log base 5 of x plus 6, to rewrite this in its inverse form, we just switch the x's and the y's. So now this becomes x is equal to log base 5 of y plus 6. When we solve this, we're solving for y, okay? Y is what I want to get it equal to, but y is hiding in this argument position, all right? I can't just get it out of there. It's just like when we had the variable hiding in our trig phase, right? We couldn't just get it out of there. All right, so what would I need to do here? One of the ways is to take this and rewrite it from its log form into its exponential form, okay? Let's try that. We have a base 5 raised to the x power equal to the argument of y plus 6, right? Isn't that what we practiced above? base 5 equal to the exponent, or base 5 raised to the exponent equal to the argument. Now y is not hiding in the argument position anymore. It's clear, it's free for us to be able to do anything with, and we would subtract 6 to the left-hand side. So I would have 5 to the x power minus 6 is equal to y. So the inverse of our original log 5 function is 5 to the x minus 6. What does this minus 6 do? Moves it down, doesn't it? Moves it down. All right, let's see if we can graph it over here on the same thing. See what that would look like. 1, 2, 3, 4, 5, 6. So we moved our horizontal asymptote. To y equals 6. We have an x-intercept, or excuse me, a y-intercept that occurs at -5. And it would go like that. Now, squint your eyes, tilt your head sideways, and imagine a y equals x line right here, right? This thing is symmetric across that y equals x line, isn't it? Okay, if you can kind of see that, I don't want to add more to our graph, but these two things are inverted or inverses of each other. This is my favorite test question. Give you a log or an exponential function, have you find information out about it, and then tell me what the inverse of the function is. Okay? What does that typically mean? If a teacher tells you that that's her favorite test question?
It's gonna be on the test.
You know how many people miss that question on a test? Prove me wrong. Prove me wrong this semester, okay? Because the track record's not very good. All right. Let's look at this application here. Oh, this is a funny one. Students participating in a psychology experiment attended several lectures on a subject and were given an exam. Every month for a year after the exam, they were retested to see how much of the material they remembered. The average scores are given by the human memory model, where T is in time in months. Okay, so we have this log function that says 75 minus 6 times the natural log of t plus 1. And I want to know what are the values, right? I want to know what are the values at these various points. Let's just use our calculator for this. I think this would be an easy one to use our calculators for. So what is the average score on the original function? What is the average score 2 months after? And what's the average score? This is a model, right? Okay, so we have the function 75 minus the natural log of x plus 1 is what we would put in our calculators, right? Not t, x. In other words, how will I know what the score was after 0 months, 2 months, and 6 months? Am I not just evaluating the function at those 3 values? Yeah. Yeah.
Easy money. We got 75. 2 months, 68.4. 6.63.
Where did the natural log come from?
It was this whole thing that I have highlighted in yellow, was just given to us in the equation.
I meant like, just like,
Oh,
Is that-
where did somebody come up with the natural
well,
log?
E. but it's like the number,
Oh, that's kind of one of those, B or phi. I always think I'm saying it wrong, P phi full thumb, right? B is the golden ratio,
Yeah,
and I don't
Okay.
remember what number that is.
yeah.
So who did that one? Back with Pythagorean and all the Pythagoreans? I would imagine that's where, because if you look at how E is figured out, where it's a recursion, it's a sequence, I think it's the same. I know, and I haven't read up on it in a while, logs were, somebody made logs to make it easier. Okay, it was in the 20th century that they decided, I feel like it was the 20th century or the late 19th century. Came up with logs as a way to do something. It was easier for them to do something. I haven't read on that one in a while. All right, do we have values here?
Yes,
Yeah,
on the original, it's 75.
okay. So the average score on this test was 75 after they took it, right? With 0 time elapsed, it was 75. After 2 months, what was the score? 68.4. After 3 months, after 6 months, what was the score?
63.2.
63.2,
Oh, that's
right? So here is a graph of that function, right? That would be a decreasing function, wouldn't it?
63.32.
Okay, well, whatever, 63.2, okay? That's a decreasing function, isn't it? What does that tell you? Because this shows up in every textbook I've ever taught for logs, this question always shows up as far as memory and how much we retain of something. What's happening? There's a steep drop off, right?
Yes.
Of what you're gonna remember after this class, and then it might level out, okay? Keep that in mind, right? This is why you try to study to put things in the long-term memory and not in the short-term memory, okay? As you move through, all right? I always thought that's a funny example. Okay. Any questions on logs and exponents? Pretty straightforward? Just gotta go practice them? Yeah? Okay, good, we're done today. No Zoom, no